model, yes, because the point is that essentially they coincides perfectly at the map. They intersect at the map, the Gaussian, but for this other one, no, I mean, yeah, in order to get this, actually it's going to with the other domain, is the original one.
Yeah, let's stay in touch, From time to time I get the feeling that Meta is now already more now I have so many positions there that it kind of does not look good. So maybe for a Europe and a UK, I don't have a keen on it.
I'm restructuring the house. So you go in a conference and then I go back home on the weekend to suffer. Just, oh my god, it's complaining with the administrator of the condominium because I'm changing the window. They keep it the same color, but they want like full time and stuff. So it's kind of outstanding things that you think are easy, but then it's money. Okay, we see you again. Thanks. Congrats for the work. Thank you. Yeah, let's go. No, I wasn't trained to pick up. I'm studying now.
I got to your poster. Sure, thank you.
Hey, join Maxime. So you were doing it's another paper.
Bayesian generalized model. That's just where your predictors are complicated functions that they covariates. But you essentially use you learn them on the go also. But this is kind of a wrapper we use a genetically modified MCMC there. So, yeah. No, we're trying to learn them. Yeah, those papers I can share. Yeah. So the one that I mentioned that is related somewhat to this nice work that you
Okay. Yes, they turn it off, and yeah, that should be okay. Okay, but and in case you also have this, so people can, but at the moment they cannot see it there. They just can't just see it on YouTube. Yeah, yeah. Okay. Yeah, now it should be off. No, okay. So this will be off as well, and let me. People can see and hear you from YouTube. Okay. Okay, so you don't need a point. Well, because they are messing up with the YouTube, so I go.
Oh, hey. I can tell them the story. Hey. Let's see, is this, can you all hear me? Let's see, how's this? Is this better? Is this, I wanna tell you all a story.
Andrew has a story to tell us all.
Yeah, we have this idea, it's called, I'm all excited about, called the Squealer. So the story was that, well, I had a colleague who was blind, an economist, and it got me thinking about developing statistical methods for the equivalent of visualization for people who had sight impairment. And so you can have like some ideas of, like for example, you could have a scatter plot and put it on some sort of pin board and you could feel it with your hand. And I don't know, none of these didn't quite work out, partly because sight conveys so much information. It's hard to use different senses to convey that, but then we realized that other senses have advantages that sight doesn't have. So sound conveys a lot less information than sight, but you don't need to pay attention to hear a sound. Like for example, when I'm talking and that alarm goes off, you won't be needing to listen to that for that alarm, and you'll still hear it. And then the haptic sense of resistance has a kind of continuous nature. It just feels different. It affects us in a different way than the visual sense. So we moved toward this idea of developing not statistical tools for visualization for blind people, but use sensifications using other senses to help sighted people learn better. And so I had this idea, and it goes like this. Suppose you fit a model, for simplicity, say it's logistic regression to some data, and you have a scatter plot with the data. You all can hear me? You have a scatter plot with the data, and then you have the fitted logistic curve, and you fit it in Stan, and you have a bunch of uncertainty curves. And then next to it, you have another plot, which is a scatter plot of the posterior simulations of the parameter values. So there's a point estimate, like a posterior mode here, or posterior median, say, and then a bunch of dots. That's like, let's say blue, the posterior median. Then a bunch of little red dots indicating posterior simulation draws. On this graph, you have the data, and you have a solid blue curve showing the best fit curve, and then a bunch of light curves showing other possible. So what I wanted to do was build some sort of widget where you grab the curve in two places, and then you can move the curve. And as you move the curve, depending on how you push it, the kind of gradient moves it, but it keeps it in the space of the fitted model. So what you're actually doing is moving this point around the estimated curve. You could even directly move the point around, but I feel it more compelling to move the fitted curve around. And then the idea is that as I move the fitted curve around, as I go to areas of lower posterior density, I feel pain, right? Like I have to push harder. So I have this kind of haptic controller with a couple of joysticks, and I'm moving it, and if I try, now this sounds kind of goofy, but this is not just for teaching, like, hey, we're trying to teach this stuff, blah, blah, blah. This is for applied research, because often, like I'm doing this project with Qixuan at Columbia, where we're fitting models to dilution assays. And it's kind of weird, because sometimes you look at the data, the best fit curve doesn't look like it fits the data perfectly. It looks like you should do something better. You could do something better. And I really want to grab the curve and move it, but then I want to feel this resistance. So I had a summer student who was an engineering student from the University of Michigan, a guy named Sam. And I said, build this haptic controller. And so we talked for a while, and he said, that's not the right thing to do. He said the first thing to do is forget all the haptic stuff, because that's heavy hardware. Start with something simple, where instead of using joysticks, you're just moving stuff with the mouse and the keyboard, and then instead of the haptic resistance, have it make a sound. So as you move further and further away from the mode of the posterior density, it starts making a noise, a high-pitched noise, hence the squealer. right? So then if we could get the Squealer working, I wish I had a Squealer demo for you, but he hasn't built the demo yet, like we're still working on it. But then what you could do is move the curve around and see it squeal. And then if that worked and it made sense, we could build the haptic demo. But I think that could really improve my statistical practice. And I'm super excited about it. Also, I just like that it's called the Squealer. And I think there's a lot of, anyway, I just wanted to share that with you. I didn't want to waste any of my talk on that because it doesn't exist yet. So I just wanted to share that to you while you were waiting.
Well, it reminds me of when my kids were little and they'd ask for a bedtime story, right? And I would tell them a story, but they wouldn't go to sleep. It was a bad idea. Andrew gave us a wonderful story, right, about the Squealer and the kind of thing that, that just typifies him. Right, just an incredible creativity, originality, which is part of what Andrew has brought to the world of statistics. I see that there's an enormous number of people standing at the back, and as long as the fire code is okay with it, I think it's wonderful, because the hope is to have this be a real session where Andrew tells us his view on things, but also there's reactions, and by all means, feel free to ask questions. The dialogue should be interesting and just fun for everyone. There's so much to say about Andrew and all he's brought to the world of statistics and Bayesian statistics, but beyond Bayes, that I could go on and on about huge awards like the COPS Award and different positions in different places, Stan and the impact that that's had on the entirety of the Bayesian discipline within statistics, but I think even more so outside of the narrow confines of statistics is really, really remarkable. And, beyond that, I'm just going to say he is a guy who truly needs no introduction. So I'll turn it over to Andrew, and he'll talk for a while, and then hopefully a wonderful dialogue. Ask questions. If you're in the overflow room, I don't think you can ask questions, but you could run over and knock on the door and then ask questions. Andrew?
Thank you. So one thing I've learned from the computer scientists is to do a lot of experiments. It's partly just the term. So when they're writing, a computer scientist is writing a paper and they have some, what I would call statistical method or some method, they say, now we're going to run some experiments, which is great. And we didn't used to say that. I don't remember what we used to call it. I mean, but we would, I guess, maybe say we were doing simulations or something. But I really like this idea of experimentation. And I think I got some of this from Bob Carpenter, because when we would have some argument, then he would just go to the computer and run an experiment and tell me what happened. And I was like, yeah, of course, I could have done that. So now I'm doing more of that. Even in simple cases, I'll give you a very simple example. After my, a couple of years ago, I was teaching a class at the end of the semester. I had the final exam. It was a multiple choice exam. People think that's kind of silly, but there is some principle that the more effort you put into creating the exam, the less effort you have to put into grading it, which sounds kind of cynical, but I'll flip it around and say, if you set up an exam that's really easy. Okay, if you set up an exam that's easy to grade, you can only do that by putting a lot of effort into it. So it's actually good. So I'm a big fan of multiple choice exams. My colleagues, my psychometrics colleagues, always do item response analysis to check that the exam questions have positive discrimination. And I wanted to do that, but I also knew that the next semester I'd be teaching logistic regression, among other things. I didn't want to start by an item response model, so I fit something very simple. For each student, the predictor is their total score in the exam, and then for each exam question, I fit a logistic regression predicting whether they get the item correct, given their total score. And then I just ran it. There are 24 questions in the exam, so I looped it, ran it 24 times, fit the model, had the data, drew the curves. It's hard to see much. Then you reorder the questions in decreasing order of percent correct, and you see some of the questions had negative discrimination, which was kind of weird. Like, it can happen, right? Like, right? Like, if it's a trick question, or it's too easy, or this and that. But then I looked more carefully and I'd miscoded 3 of the questions out of 24. Like it just, yeah. Okay, so I checked all 24 and then I redid it. Fortunately, I did it before handing in the grades because I was already preparing for the next semester. So all good. Then when I did it, I fit the model. It was great. It's in our active statistics book, that example. Then later, the year after I was teaching Bayesian statistics, I thought I'll just do the same thing, but I'll play around with the model a little bit. So I fit the model in Stan, and then we fit the logistic regression model with guessing. So the probability goes, instead of going from 0 to 1, it goes from 0.25 to 1. And you can fit that to the data. And then I had this principle, I should always simulate fake data for anything I'm fitting. So I simulate some fake data for the model. I'm preparing this like computer demo for class ahead of time. And I simulate fake data for the model and I fit it and it works fine in Stan. So it's all set. So I go to class and do it and it doesn't work, which makes me remember whenever I'm doing an example for class, I also should fix the seed ahead of time. So I learned something here. It was funny, it fit the data, but not this. You know, statistics is the science of defaults. And things don't work every time. So I started playing around with this more. I won't give you the full story, but there's another idea that's we've used for many years, which is the robust logistic regression model, where instead of having the probability go from 0 to 1, you have it go from 0.01 to 0.99. Now you can use that in a lot of examples, because there are a lot of problems where like you might be modeling voting or Supreme Court decisions with an ideal point model, or you know, what movie people want to see, whatever it is. You often can have a situation where someone is predicted to have a probability very close to 0 or 1, but they don't follow it. Like there's kind of a 1% chance people do the wrong thing. And so I feel like in general we should be fitting this model, not logistic regression. We should always be doing it. But then I was finding some issues. And the problem is that even with a 1% chance, well, first let me say the good thing about this robust model. There are 2 good things. One is obviously it doesn't overfit to these bad points and allows for the occasional error or miscoding or whatever it is, which is really great in practice. And it flags it too. Like you see it and you see a high probability of being in that mixture component, and they can go back and look at the data. So mixture models are great. The other thing that's good is that by cleaning out the bad things, it allows you to much more precisely fit the mass of the distribution. So paradoxically, you get a sharper inference for the part that's not categorized as a mistake in some way. I mean, this is well known, but it's kind of, some of it was kind of new to me when I was doing this. So this is really wonderful. One problem, though, you can get computationally with something like Stan, because it's kind of too good that it explores the posterior distribution, is there is a small but non-zero chance that you can categorize all of the zeros and ones as misclassifications, which means, or almost all of them, which means you can end up fitting the logistic regression component to as arbitrarily small part of the data. In particular, you can fit it to an arbitrarily small part of the data that shows complete separation, giving you an infinite slope, or an infinite negative slope in the other direction. It's not likely that that happens, but it's there, and if you have a flat prior, then your Stan, well, it should find it, and if it doesn't find it, it's kind of a computational problem. It turns out when you do simulations, this will turn up. And you can solve this problem by putting an informative prior on the logistic regression coefficients. For that, I recommend rescaling the predictor first. Otherwise, it's super hard to have any intuition for what that is. And then to really understand the informative prior, you can do prior predictive simulation, which gets back to where we started. So I purposely started with a very simple example to illustrate just how much we learn from experimenting. Before getting to my main talk, I wanted to tell you about the project that I'm the most excited about right now. It's something I'm working on with Yajuan, which is incorporating sampling weights into regression model and Bayesian inference. And so it goes like this. Sometimes we're interested in, well, like there's some elections coming up around the world, and we're interested in local voting. We might want to know how people vote in individual states or individual districts in a country, and we have a national poll, so we can use multi-level regression and post-stratification, we can model the people's political preferences given their geography and their demographics, and then having done that, post-stratify and get predictions for everyone in the population based on their demographics, which could be framed as a post-stratification table or a voter file. And that works pretty well. It's not perfect, but when it's not perfect, you can try to post-stratify in more things and so forth. I think it's a good direction to go. I like it. But often we have surveys and they come with sampling weights. And the idea is that if you take the unweighted average of the survey, you'll get the wrong answer. You want to adjust for the sampling weights. It's not clear how to do that in a Bayesian framework or a multi-level regression and post-stratification framework. So for example, let's suppose we have a survey and you have a weight of 1 and you have a weight of 4. Okay, what does that mean? Well, it kind of means that you represent 1 person in the population and you represent 4 people. Or you represent 1,000 people and you represent 4,000 people, whatever it is. You represent 4 times as many people. So the very natural thing to do would be to run the regression, fit your model, and just power up your likelihood by 4 because you represent 4 people. Well, okay, it's a little tricky because I could power up your likelihood by 100 and yours by 400. Like that won't affect your maximum likelihood estimate, but will affect your Bayesian inference. So you have to kind of figure that out. But conceptually, it sounds kind of right, but it's wrong. And it's wrong because if you have a weight of 4, that means there are 4 people like you in terms of your predictors in your population. There aren't 4 people like you in terms of your outcome. It's not that there are 4 of you, it's that there are 4 people like you. So if I weight your likelihood by 4, I'm actually overstating the information I have because I'm acting as if not that you represent 4 people with your demographics, but that you represent 4 people with your survey response. And if that's not actually what's happening. And even if you rescale, that will be a problem. So we had this idea, which was to include post-stratify. If I have a model which is y given x, that's my regression, my multi-level regression model. Has to be multi-level because I have a lot of predictors in x because I want to adjust for many things. Just by the way, like back in the day, these Bayesian conferences, people used to talk about Occam's razor. This is a horrible idea, like how justifying simplicity of your model. I'll tell you, in all my years as an applied statistician, in my many decades, and also as a physicist, political scientist, nobody has ever come up to me and said, hey, you see that model you have? Could you take that variable out? They're always like, why didn't you include that? Why didn't you include that? Never, yeah, I mean, so, yeah, what's it, the term they use, parsimony is, yeah, it's a ridiculous idea. We don't want a justification for it. Fortunately, there is no good Bayesian justification for it, so really no problem. So we want to adjust for a lot of things, which motivates multi-level modeling. So we're going to regress y and x, but now we have a sampling weight, w. So what I really want to do is post-stratify on y on x and w. So the amazing thing, what we realized is that it's not that hard because post-stratifying is hard, but I'm only adding 1 dimension to my post-stratification problem. Now the only thing is I don't have a table of x and w in the population. In fact, W doesn't even exist in the population because the weights are a function of the data. So this is a kind of quasi-Bayesian approach in that we are modeling the data as if they are inverse probability sampled from a population, so there's a population distribution of weights, even though that doesn't exist, but we're acting as if it does. So we now need to regress y and x and w, which is very easy. I just add one more thing. We also now need the post-stratification distribution of x and w, which means we actually need to estimate the population distribution of w given x, the distribution of the weights given the predictors. This is really cool. This is one of these wonderful Bayesian things where the math just does what you want. Because once you frame it that way, you need to model the weights given the predictors, which is perfect because if the weights entirely depend on your predictors, you don't need to do weighted estimation, which is something that sample survey people know. It only comes up when there's information in the weights, not in the predictors. So what we're actually doing is it's not that you have a weight of 4 and you have a weight of 1. What's relevant is your relative weights conditional on your post-stratification cells. And so we can do that. We actually, believe it or not, we do this using bootstrapping inside a STAN program. And like maybe I thought I'd never be using bootstrapping. You do a weighted bootstrap. So if you have a higher weight, you're more likely to be resampled in the bootstrap, which exactly adjusts well, I shouldn't say exactly, it adjusts mathematically for the weights being inverse probabilities. And I think we can do this with causal inference too, so I'm super excited. But here's the funny thing about bootstrapping, why it works here, okay? Because it works for the reason that bootstrapping often doesn't work. So the problem with bootstrapping is that it does not take you beyond the range of the data, right? So when you have sparse data and you bootstrap, you're only getting replicates of the data you saw. So you don't see anything in the tail or beyond what you've actually seen. And that's well known to be an issue with bootstrapping, that you have to aggregate enough data that if your sample is too small, then you're missing things and you have holes and you're never filling them in. But in this case, that's actually a plus. This is a bug that's actually a feature in this case. And the reason is, if you are trying to estimate, if you're trying to resample inverse probability weights from a latent distribution, what if there's a weight, somebody in the population with a weight of 1 trillion, but they only have a 1 in a billion chance of, 1 in a trillion chance of being sampled? But they could be there, right? So there's this long tail of potential weights, sort of like in astronomy, the stars that you can't see, like what's the distribution of all the stars far enough away? And you need to, if you don't model that right, it turns out that tail will wag the dog of the inferences. Because not the left tail of small weights, it doesn't matter, but the big weights that aren't there in your data, that will have, it turns out, did some experiments, that it turns out that will be very influential. So if I bootstrap, I don't get that long tail. Now, if I'm doing importance weighting, like we do in Bayesian computation, we have importance weights, and we're trying to deal with that, you need to deal with the long tail, because you're worried about missing that. But survey weighting is different, because remember, the survey weights aren't real things. They're just constructed. There is no long tail. There isn't someone with a weight of 1 billion. The inference is conditional on the weighting procedure that you're doing. So you don't actually want those. So in this case, the bootstrapping actually works. Well, we're still not all there. We're bootstrapping residuals from a regression model, which is super great. But when you look at things carefully, you realize that within post-stratification cells, your variance, you might be concerned that the variance of the weights could vary by cell as well as the mean of the weights. So you really want to do something like a local bootstrap. There's some literature on this where when you bootstrap, you're more likely to sample things in your cell or near your cell, which is almost a kind of modeling itself. So we're kind of moving in that direction a little bit. So more needs to be done. I just wanted to share that with you because I'm so excited about it. I love this project so much. Okay, it's an honor to speak here. The first Bayesian meeting I came to was in 1991, and I was very upset at the time. It made me really miserable, actually, this meeting. People were very nice, but I kept going to talk after talk and looking at the posters, and people were really into this subjectivity. They'd have some model, and they'd say, well, like, what about this model? Do you want to check your model? They'd say, no, we're not going to check it. So why not? Because it's subjective. So it's subjective, so you can't check it. And like I thought, that's wrong. It's the opposite, right? If it's subjective, you should want to check your model. That's the whole idea. But there was a real ideology. And the ideology was there was no such thing as model checking, that it wasn't allowed. It was really, people were really not allowing themselves to check their model. They felt it violated the principles of subjectivity. And it really, really annoyed me. I remember going to more than one, I remember one poster I went to and it was a very interesting model. They were modeling people's patterns at night, like their different stages of sleep. And they had some data where they did some sampling. I think they'd wake people up at random times, and they had data on when people were awake or asleep, and then they had a Markov model over time. And they fit it, and they had their estimates of how long people were in different aspects of sleep. And I said, this is really cool. Could you simulate data from your fitted model? I just want to see what your simulation of the time series process looks like. Is it flickering, or is it, I don't want to see your posterior mean. I want to see your actual simulation. And like, really, what's that? That was their reaction. So I was really upset. And I just thought, okay, no more Bayes for me. And I had been doing a project where we were doing model checking, and I just framed it in very non-Bayesian ways. So we're trying to do a chi-squared test. It was a problem for medical imaging for my PhD thesis, where you're trying to estimate a high-dimensional image. I think in this case, you could imagine the image has 20,000 pixels, and you have, let's say it was 10,000 pixels, and you had 20,000 data points. The data points were these line integrals that came from the machine. Well, I have 20,000 data points, which are supposed to be kind of Poisson distributed, and I fit the model, and I want to check the fit of the model to the data so I can compute a chi-squared statistic with 20,000 degrees of freedom. It's 20,000 minus the number of parameters degrees of freedom. So is it 10,000? Well, it's not quite 10,000 because there's a constraint. Although I have an image with 10,000 pixels, the image is constrained to be positive. And the positivity constraint implies that if you know about a few pixels, it tells you about other pixels. You don't have 10,000 free parameters. How many free parameters do you have? It's tricky. It kind of depends on your data. It's an interesting problem. So I did some work on it, and I had this idea. So it's a Bayesian method for getting better chi-square test. I can't remember what I called it, but it was something like that. So we're using Bayesian inference, but chill out, people. We're not really being Bayesian. We're just trying to get a better chi-square test. And the non-Bayesians they didn't hate this. They just ignored it. Because I was using Bayesian method. That's cheating, right? I should have just said I came up with this method. It's a statistical method. And then they would have loved it. But I made the mistake of not erasing, not removing the scaffolding first. Now, then I talked to the Bayesians about it, and they hated it too. But, well, maybe they should have. I don't compute p-values anymore. But they hated it, but at least they listened. They were interested. So I really appreciate the Bayesians who might hate what I do, but listen, and give me good reasons why I'm wrong. So I think that's really great. So thank you all for all of that. I appreciate all these years. Statistics all about generalization, right? The goal is to generalize from the sample to the population, from the treatment to the control group, from observed data to the latent quantities of interest, constructs that you care about. To do this adjustment, to do this generalization, we need to adjust for many factors. In fact, more and more I'm thinking that, well, they say they're Euclid has 5 axioms, but you don't have to take those 5 axioms. You can take any 5 true statements about geometry, and they can be the axioms. And I think this comes up in analysis too, various theorems, Bolzano-Weierstrass theorem or things like that can be taken as axioms, and then other things that are axioms can be taken as the theorem. It's just like a macrame sculpture. You just grab somewhere and see what's hanging. I've been thinking that adjustment is a primitive in statistics. We tend to think of adjustment as we do inference and we can call it adjustment, but arguably so much of statistics, if you think of the key tasks of statistics, there's design of experiments and surveying, data gathering, data collection, measurement. Adjustment is one of the things we do. So I don't know, I feel that it's super important. And when we think about adjustment as kind of one of the things we do as statisticians, that leads us to adjusting for many factors, which leads us to some sort of regularization. It doesn't have to be Bayesian, but some approach for adjusting for a lot of things. I wanted to now briefly give my main talk, which was I wanted to list some holes in Bayesian statistics. Now, these can be thought of as holes in Bayesian theory, where practice has to kind of go beyond, or they can be considered as holes in Bayesian practice where the practice doesn't line up with theory. And this is some work I did with Yu Ling. And my goal here is to kind of get you a little bit upset and to point to open problems, but also kind of point to the idea that these holes can be a good thing, that it's actually to mix metaphors, we can use the holes as leverage to do better. So very briefly, the first hole is something I learned when I was in college. I was a physics major from quantum mechanics, and that's the laws of probability are not true. And this is just well known. So in physics, what we call the laws of probability, like Kolmogorov's axioms, are called Boltzmann statistics. But actual subatomic particles follow Bose-Einstein statistics or Fermi-Dirac statistics. They just don't follow the laws of probability. They're not like dice and so forth. Another example is the two-slit experiment. So I send some photons onto a thingy, I don't know what it's called, a screen that has two slits, so the photon could go through this slit or this slit. Then there's a screen here where it hits and it lights it up. And I can do different experiments. I can close one slit and then look at what happens, and I get a nice little curve of a little bit of spread of the photons through the slit. I could close the other slit, and I get a little distribution like that. I could run the experiment with where both slits are open. No, that's cheating. I could run the experiment where both slits are open, but I have a detector saying which slit the photon goes through, and then I'll get a mixture distribution where it's some of this and some of this, just like you would expect. Or I can run both slits open. You can do it for reals, or Google it. That's even easier. And you have both slits open, no detector, and then you see this weird pattern that looks like this with actual nodes or blank spots. So the point is, the laws of conditional probability say that the distribution, not knowing which slit it goes through, is an average over a mixture of the distribution of slit 1 and slit 2, and it's not. It's wrong. The laws of probability are false. This is well known that if you don't measure which slit it goes through, then the slit it goes through is not a latent variable. It does not go through one slit or the other. It goes through both slits, and it interferes. Now, when I say this example, I think a lot of people are like, yeah, you're right. And then other people, no, it's a different problem because you have to condition on whether you have a measurement at the slit or not. And that's correct. So you can incorporate the two-slit experiment into Bayesian theory, probability theory, by merely adding that information. The point is that we don't do that usually, right? So usually when we do Bayesian statistics, we say we observe X, we observe, there's A and B, the probability of A given B, we observe B. We don't say the probability of A given B and comma, we measured B. Right? We don't do that. So yes, you can do that, but we never do. So the Bayesian theory, I think implicit part of Bayesian theory or practice is that we assume that anything not measured is a latent variable. That's it, and you can't actually do that. So that's false. What it means for practice, I'm not sure. Sometimes, like in toxicology and pharmacology, we have latent variables. So I'm doing an experiment on dosing, and the latent variable is what's the concentration of a drug at a certain, within internal compartments in my body. Here I am pointing to internal compartments in my body. I think that's fine. Like, that's a latent variable. It exists, and I have no problem doing Bayesian inference on that. I guess at the quantum level it would break down, but somehow I feel like a kind of classically sized person myself, so I'm not so concerned about that. On the other hand, what if this is a problem like, there's a famous example in psychology where a survey was done, and they asked people, they give you a little vignette, and the story is as follows. So you are, you're a college student, right, because you're students in the experiment, and you are offered a discount vacation ticket. You can fly to Bermuda and have a wonderful vacation, and the vacation is going to happen a week after final exams, so finals are coming up. Would you take this? Like for $300, would you buy this discount ticket and go? And a lot of people say, no, I can't go because I'm too frazzled. Like I'm focusing on my exam. I can't do that. But then they give people the two-slit. They say, okay, some people get this. You're going to do this, and you are going to fail the exam. Then you can take the vacation as a way to make yourself feel better. Or you're going to pass the exam, and then you're going to take a vacation as a way to celebrate. And under either situation, people will take the vacation. Well, not everybody, but like there's more people will take it. So conditional on the outcome, more people will take it than unconditional. Now, the question is, should I think of that as an anomaly? Maybe I should do a quantum model for this? Like I should, so here it's kind of pretty clear that telling them the exam result actually does change how people think, but that actually violates classical utility theory, under which preferences all exist. But we know, those of us who work in social science know that survey responses are survey responses. Preferences for most things don't exist until you ask the question. You do not actually have a favorite flavor of X. We can ask you a question, and by asking you that stimulates a certain thought process. So I think there's something deep going on there. That's example number one. Hole number one. Hole number two in Bayesian statistics, this is my favorite example. Some of you might have heard this before. You do an experiment, get an unbiased estimate of some treatment effect. Whatever it is, pick your area of application. Unbiased estimate of the treatment effect, and for real, no cheating, it's all pre-registered, blah, 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 whatever, it's all kosher. Your estimate's one standard error away from zero. So as an applied statistician, no joke, I know what to say, which is that's consistent with noise. It's a certain amount of information, but I wouldn't take it so seriously. On the other hand, suppose I was a kind of naive chatbot who had read Bayesian data analysis and followed it and thought that that was how to do statistics. Bayesian Data Analysis is the book that we wrote, and in that book we kind of have a lot of flat priors. So reading Bayesian Data Analysis, I set a flat prior, because what do I know? There's no context. I just said it's some experiment. So I do that. So then my posterior distribution is that my posterior mean is one standard error away from zero, one posterior standard deviation away from zero. Assuming we have enough data that we can estimate the variance well, it's normally distributed, that means that there is an 84% posterior probability that the treatment has a positive effect, which means that I should be willing to bet 5-to-1 odds that the treatment works. Okay, now willingness to bet is a funny thing because to bet, you need a counterparty, and the fact that someone's offering the bet means they might know some information. So, I do not think betting is the world's greatest foundation for probability. That's another story. We talked about foundations of probability another time. Betting is a model for probability. Rolling dice is a model for probability. There's a lot of different models. No single model covers all of it. That said, if I'm being Bayesian, I would act as if there's a 5-to-1 odds, which at the very least means if someone were offering me a bet and I didn't think they had a lot of extra information, that it wouldn't be unreasonable to take it. And maybe I'd take 4-to-1 odds. That would be bad. As practice, as a way of life, if every time I saw an estimate that's one standard error away from zero, I act as if I am 5-6 sure that the treatment has a positive effect, I think I'd be wrong there. I think that would be a mistake. Now, that's a hole in Bayesian statistics. Well, the hole is that I shouldn't be using the flat prior, but even a weak prior, like a normal 0-100 prior, that would still have this problem. It's not about the improper prior. I have prior information. It's a kind of by a sort of anthropic principle. The very fact that I even said it was one standard error away from zero implies a kind of zero centering, a kind of zero importance. Let me put it another way. What if I weighed you on a scale and you weighed 80 kilograms? What if I said your weight was 80 kilograms with a standard error of 1 kilogram. It's the standard deviation of the scale. Would I say, oh, you're only 1 standard error away from 79 kilograms? I can't reject that you're, no, of course not. There's nothing special about 79, well, unless there was for you, but like in the abstract. So the very fact that I'm saying that conveys information, which is kind of a little like that, I never thought about this before, but it's a little bit like that two-slit experiment, that the measurement, the way the problem was framed contains information in there. And I don't know, like, I do think this is a hole in Bayesian statistics because we've been recommending flat priors. How do we deal with this? So the way Bayesians deal with this is by, and I want to say it's a problem. Okay, so there's 2 ways we deal with it. One is to just not make these statements. So we don't go around saying we're 84% sure that the treatment works. We do stuff like report 95% posterior intervals and say that they overlap with 0, and so we're not really sure. Like, we don't act as if it is. So you know what, it's like, okay, it's like Bayesian inference gives you inference for everything. So it's like a minefield where you have to walk around all of the suspect inferences until you get to the ones that you can believe in. The other thing that we do is we believe it, but we don't really believe it. So for example, what if something is 2 standard errors away from 0? So it's statistically, in the posterior distribution, 2 standard errors away from 0. So we do not, oh yeah, we're like, okay, yeah, I believe that. But do we act as if we're 40-to-1 odds in favor of that? Not really. We know that things are statistically significant, like more than 1 time out of 40, something is wrong. But it's not even something being wrong with the model. Just that being 2 standard errors away doesn't convey as much information as you'd think, which you'd immediately see if you put informative priors on. So the way we handle these things is to not really take our numbers completely seriously. We're not really giving numbers we would bet on, even though we sometimes say that we would. And that's a hole in Bayesian statistics. The one reason why this is a problem is that when you get in the habit of saying stuff you don't believe, then when you get numbers that you do believe, you're not sure how to use them. Because sometimes I've worked on problems where I actually have a strong prior that I do believe. I don't believe, but like I believe it in my model, the same sense that I believe my linear regression or my logistic regression or whatever. Like I'm willing to hold that as my model. The same way as if I'm doing a cost-benefit analysis for the local planning commission and I put in a bunch of numbers like how much does it cost to hire people and how long do we have to wait until blah, blah, blah. They're supposed to represent real numbers that I'm putting down, right? When I do that, then when something's 1 standard posterior standard deviation away from 0, I really should be there. And I'm in the habit of not. So I'm in the habit, I believe, are in the habit of doing Bayesian inference. What was that? We are in the habit of doing Bayesian inference and getting posterior distributions, and even when we do it right, not trusting them, not taking ourselves seriously. So that's the price you pay. So the price you pay for going around giving out numbers you don't believe is that when you give numbers you do believe, you end up acting as if you don't. So I'll see things, if I'm really doing the Bayesian inference and I'm 1 standard error away from 0, and my 95% interval contains 0, I should still act real, I should be pretty damn certain, like 5-to-1 odds. So it works both ways. It's a little like what I was saying about our mixture model earlier, that like when you have this error mode, it kind of degrades performance all over. This reminds me of something, because there's a saying about decision analysis, which you might have heard. There's a story where some decision, okay, if you look at old decision analysis textbooks and articles from back in like in the 60s, it was really, really big, 50s and 60s, even the 40s, you'd see 3 kinds of examples. The books are always full of these examples like, your nephew is going to college and he's trying to decide whether to live on campus or off campus. The on-campus apartment costs more, but it's closer, and so he has to balance his utility. It's all these bogus problems like this. They're all fake, uninteresting, bogus problems, widgets, right? Okay, that's example one. The second kind of example is military examples. Oh yeah, we did this stuff for the military, we can't tell you anything about it. So that's like old statistics textbooks. We did all this cool stuff for the military, but we're gonna give you examples with widgets and probability distributions. The other is business examples. Oh yeah, we're helping some company design put their new plant, but it's private, so we can't tell you. So like they're trying to get all of the kind of glamour from these examples, but they won't share it to you. So we can do better nowadays. But there was a saying that a story, supposedly some decision analyst had an important life decision to make, whether to take a new job or move to a new city or buy a certain car, or whatever it is. And telling his colleague, and his colleague said, oh, well, you do decision analysis, lay out the costs and benefits of probabilities. And supposedly the decision analyst said, are you kidding? This is serious. You know, and it's like, well, no. So then there's like, why do we do Bayesian decision analysis? Like, I make this assumption, this assumption, this assumption, and that says, okay, this is what you should do. Well, I don't like this decision, so I'm going to go back and change my assumption. So what's the point of doing anything? Well, the point of doing anything, this is kind of important, is that, I mean, there's a couple things. One is we're doing what we call institutional decisions. The point of decision analysis is not to make a decision. To make a decision, you can get anybody to do it. The point is to have a logic connecting to the assumptions, from the assumptions to the decision. So if you don't like the decision, you can go back and see what you don't like about the hypotheses, and you kind of force a rigor to it. And so that's the way I feel like the holes in Bayesian statistics are actually, we can leverage them. Again, the incoherence that we have is a strength in that we can kind of lean on the incoherence, and we can say, this is wrong, so what part of our model needs to be better? And we have to be willing to do that. Okay, I have some other examples, although of holes. Well, okay, I'll go through quickly. There's the incoherence of subjective Bayesian updating. This is really something that from when I went to the Bayesian conference in 1991. So you guys maybe don't need to hear this anymore. But back in the day, people would say, like, what's the prior? Well, it's my subjective belief. And then I would always say, like, where did that logistic regression come from? Was that your subjective belief too? And they would go, yeah, sure, you know, fine. Okay. And so Bayesian inference, the paradigm of Bayesian inference, which there's a hole here I'm telling, because the subjective paradigm of Bayesian inference is you have a subjective prior, or more generally a subjective model, and then you get your data, and then you have your posterior. Now, the logical flaw of that is if you are able to come up with a subjective prior, why can't you come up with a subjective posterior? That is, why can't I give you data? The data, back in the day, we'd print it out, and you put the data through a shredder, and then mix it with some sort of viscous liquid, and then eat it, and you swallow the data, and process it and digest it. And then you should be able to extrude, as it were, a posterior distribution, which really your subjective posterior. That is, the same process you used to construct a subjective prior, which is to sit in a chair and think about everything you've ever heard in life, you could use to construct of course that's ridiculous. And so that points to an incoherence or a hole in subjective Bayesianism, in that the essence of subjective Bayesianism needs to be the map from the prior to the posterior, and there has to be some zone of uncertainty about the prior. Like, again, otherwise there's really no point. And that's like this idea that we say, like, traveling salesman problem, it's a problem so hard that no computer can solve it, but every salesman solves it every day, or like this subjective distribution, or Bayesian inference in general. Suppose our brains do Bayesian inference automatically all the time, and yet like it's very hard for us to do Bayesian inference. It's kind of weird. Obviously, our brains do approximate Bayesian inference. The traveling salesman does approximate, blah, blah, blah. Well, that approximation part's important. The other hole that I wanted to talk about the failure of Bayesian model averaging, but I think you all know about this enough already, that the so-called Bayes factor is highly sensitive to aspects of the prior distribution that have essentially zero impact on the posterior. Instead, we do predictive model averaging, but there's still kind of a hole there because it's not clear when you're supposed to do predictive model averaging and when to do Bayesian inference. So that's something you, Ling, and I have talked a lot about. Now, I think putting all these together, we can have catastrophic failures. And I think that makes us move, like a lot of awareness of these holes makes us particularly, it motivates us to think harder about Bayesian workflow, not merely Bayesian inference. So I wanted to give you a couple examples of things that are in Bayesian workflow which are not in Bayesian. And so Bayesian inference is you have your prior and your likelihood, and you get a posterior. Bayesian workflow is everything else. So one example is model checking. So taking simulations from the posterior distribution and comparing it to the observed data. It's not actually part of Bayesian inference. Indeed, you can't do it from the likelihood and prior alone. You need a data model, which is actually, the likelihood is not the same as a data model, not a data distribution. Multiple data distributions count the same likelihood, so it needs more. Another example is influence analysis. So imagine I have a scatter plot here, and I'm fitting a regression of y and x, and I have a bunch of data points here, and I have a data point here, and I fit the regression line. It just happens that the regression line goes right through this data point. Just happens. Okay. What's the influence of this data point on my fitted regression line? Well, it depends how I define influence. If I take the data point out, it doesn't change the estimated regression line at all. If I move the data point up and down, it changes the fitted regression line a lot. Well, those are inference. So this influence can be done by moving the data. Taking the data point out could be done infinitesimally, like people like Aki and Tamara work on this problem, where you consider that contribution to the likelihood as having a power of 1, and then you differentiate with respect to that power. More generally, we can do this thing of differentiating inference with respect to inputs. Very generally, what's the importance of the prior compared to the likelihood? Well, that's a kind of differential problem. My point here is that all of this influence analysis is super important. It is not part of Bayesian inference. It's part of Bayesian data analysis. Like all the things, all the stories that we do, I had a lot more stories prepared, which I don't have time for. But like even something as simple as, I have a model and I have a normal prior and I have normal data, and they're really far apart, and if I do a posterior predictive check, I can see a problem. But if I blindly do Bayesian inference, here's my prior and here's my likelihood, I'll just get something right in between, and I don't, no alarms go off. But if I were to use a T likelihood and a T prior, then I would actually get a bimodal posterior, which is just, it would be different. So where the part that's related to Bayesian data, to Bayesian workflow, is not the specific thing about the model check. It's the statement like, oh, if I do the normal distribution, the tails do this, and then this does this, and this does this. But when I do the T, the tail is a little different. And so look, when you do this. So it's actually related to this differential idea in the deep sense. But I could do a simulation study, but even I could do it analytically. That is part of Bayesian workflow, right? But it's not part of Bayesian inference. So this is a big thing. And I think a lot of what I have tried to do over the decades is take ideas that are outside the tent and bring them inside the tent. It's like take things that were considered philosophy and make them math, right? So these problems, like should I use the normal, should I use the T? Maybe we can frame it as a gradient problem. Another example, like multi-level modeling. Could talk all day about multi-level modeling. But let's just take a simple example, like our 8 schools example, where we're doing inference, we do partial pooling, And people are saying, oh, I don't know if I should do partial pooling. Like, I don't know if I believe exchangeability. It's kind of philosophical thing. So we can, it's like, for example, if I do inference and instead of 8 schools, in this example, I do 7 schools and 1 experiment on the speed of light. Well, the math is still the same. You do it. But wait, should we really be partially pooling the estimate of the speed of light to the effect of SAT coaching in schools? That doesn't make sense. It's kind of a bad model, but where did it show up in the math? Well, the math is that we assumed a normal distribution for the effect sizes. And actually, like, it makes sense for the effects in 8 schools to have approximate normal distribution because there's a bunch of small effects and they add up, and so it makes sense. A normal distribution is quite reasonable when you have a set of modest effects. On the other hand, if you might be throwing in unrelated experiments, of course you wouldn't assume a normal distribution. So I've changed it from this stupid-ass debate about exchangeability into a very specific question. Should I use the normal distribution? Maybe I should use a mixture model. Maybe I have a predictor on what the experiment is about, and so forth. Maybe I have 8 schools, and some schools are private and some are public, as they are in the experiment. I could allow those things to vary. I'm moving things inside the tent, and I think that's what we want to do, is take things that felt like philosophy and turn them more into math. I had one more story, but maybe I'll. Do you want one more, or should I stop?
It's a question for the audience.
Yeah. Do you want one more? Okay, one more. Okay, this is risk aversion. It's related to something we already talked about, which is risk aversion. I haven't written this paper yet, but I like it. Risk aversion as backdoor Bayes. Okay, and it goes as follows. You know about. Like you have a decision to make. Like, let's say it's not a medical experiment, now it's a business experiment. And I have 2 different experiments. So one thing, I do some study and I estimate a certain treatment effect. I estimate to have a 1% effect, increasing sales by 1%, which is like great, right? With a standard error of 0.1%. And I have another treatment, another thing I did, and this has an estimate treatment effect of 1% with a standard error of 1%, much more uncertain. Which should you prefer? So people will typically prefer this one. And one framing for preferring the one with the smaller uncertainty is that like, well, I'm risk averse. I want that 1%. I'd like 2%, but I'm not greedy, and I don't want the negative. I have a nonlinear utility curve. Except for most business decisions, that doesn't make sense. Most business decisions, actually 2% is twice as good as 1%. If I have one thing that's 3% and another that's minus 1%, that's like 2%. These are small, at small scales, they add up. There's no logical reason. Even if there were a logical reason for risk aversion, it would be very, very, very small. That's not a good reason. However, there might be a good reason for preferring this, and the idea is that, well, this is an estimate, right? Someone produced. If I were to use any reasonable prior, it's probably going to partially pull things towards 0. And so the 1% plus or minus 0.1% is going to pretty much stay where it is. But the one that's 1% plus or minus 1% is going to be partially pulled a lot towards 0. And so it's a lower estimate, really. Well, that's what I should do. But people don't always do that. So they can say, I'm going to be risk averse, which actually is good practice, not because risk aversion makes any sense in this context, but because it's a way of being Bayesian. Okay, well, who cares, you might say. Well, it's interesting. Now, let's take the same thing, but it's a negative effect. So some innovations have negative effects, but you still have to do it, right? You're a company, say, why would you ever do something with an effect that's minus 1%? Maybe it's legally mandated. So you need to do it, okay? Well, one way of doing it is minus 1% plus or minus 0.1. The other is minus 1% plus or minus 1. Which do you do? Well, the Bayesian rule would say minus 1% plus or minus 1% isn't as bad, probably. I would partially pull towards 0. But the risk aversion would say that actually the minus 1% plus or minus 1% is worse because you could lose 2%, unlimited downside, that's a real issue. So it will actually, being aware of this problem the Bayesian framing, even in a very simple case, can actually change the decisions you do. And if you're used to, like the usual literature is focused on positive decisions, and you're used to thinking about risk aversion, if you naively follow that to the negative decision, that won't work. Now the flip side of this, and this is the end, is that if you do a Bayesian analysis that you believe or like or trust, then you really should actually make the decision based on the expected value, because otherwise you're counting things twice. Sometimes it's in between. So I think often we do Bayesian inference with informative priors, but not fully informative. And then the question is, how does that map the decisions later? But again, my main message is that recognizing these holes should be able to help us do better in practice.
If there are questions from the audience, I know 1991 Bayes Conference, Ohio State University, MCMC.
But I was thinking of the Bayesian conference in Spain. But yeah, that one.
MCMC doesn't count as Bayes.
No, that was the second. That was the second Bayesian. No, that one I liked. That one I liked because it was all about computation. It was the Bayesian conference where people were talking about subjectivity that I didn't like.
I thought it was a different conference.
Yeah. Okay, there's a question, and then.
Is there another microphone?
Thanks for the talk. I was enjoyed hearing your perspective. Hearing what you were saying, I wonder whether you have thought about taking an imprecise probability sort of approach to problems. It seems like it may align with your philosophy.
I don't like that. I mean, at least, wait, can you hear me? Yeah, I've never seen it work. I will say, okay, this is about the foundations of probability, that I think probabilities exist in a kind of network. So my favorite example is the coin flip versus the boxer and the wrestler. So the coin flip is I flip a coin, there's a 50% probability it's heads. The boxer wrestler is the world's greatest boxer and the world's greatest wrestler get together and they have a fight to the death. Who wins? So I don't know anything, so I'm going to say 50-50. People tell me the wrestler would win, but I don't really know. So I'm going to say 50-50. Well, what does that mean? I don't know it, right? Like it's a different kind of probability. So I could say, well, actually there's a probability, P. And I don't know P, but it's uniformly distributed between 0 and 1. But that doesn't help, right? Because it's still 50-50. This used to bother me, but then I felt I had a solution to how these two problems are different. And I don't want to say they're different in that one is aleatoric probability and the other is epistemic probability. I can't do anything with that, okay? My answer is that we can distinguish these two probabilities by embedding them in a network of probability statements. So the simplest thing would be look at the probability over time. So imagine I'm plotting time, and I'm plotting the probability that my coin is heads as a function of time. I'm going to do the flip here. It's 0.5, 0.5, and then the coin's flipped. And of course, once it's in the air, you could theoretically figure it out if you have the camera. Otherwise, you kind of have to wait, and then it becomes 0 or 1. There's nothing happening before there. Similarly, I could do 1 million experiments and it wouldn't help. I could flip 1 million coins, it's still going to be 0.5. There's no information I could gather. Now, the boxer and the wrestler, again, I have the match coming up here. It started with 0.5. I can do some experiments. I can hire some people to fight. I can interview some people. I can so forth. And then I can learn and do that, and my probability will change. Or I can have other matches. So I think the key to understanding these kind of probability uncertainties is to not think of probability like chapter 1, where there's two events, A and B, whatever, is to think of the events as embedded in time or some larger context. In the same way, it's very natural for me as a social scientist, because public opinion means nothing without the social context too.
Hi, thank you. It was great. So I was wondering, because you talked about taking the philosophy into the maths, and I was thinking about the connection between the first two holes that you mentioned, that First of all, not everything that we don't observe is a latent variable, and the other one that says we tend to not trust our conclusions for analysis. And I was wondering if there's one of those unobservables there that is our own psychological setup and our own cognitive bias, and whether you think that maybe it's not just philosophical issues that we need to take into the maths, but also psychological ones.
So, okay, there's a principle that if you're going to build a table out of some wood that might be bent, the right thing to do is to measure the wood and put the table together, making account of the way that the wood is currently curved or might be expected to curve. You should not try to make everything line up and bang it into place, because then it will stretch back. So similarly, if you know ahead of time that you are not going to be following Bayesian decision analysis for whatever reasons, that could affect the inferences that you're doing. And I think I'm very interested in that topic, although I don't really know what to say about it beyond what I just said.
I was just wondering, so in all your examples, you were talking about having observed things that conflicted your priors, and each time it was a question of priors versus posteriors or whatever. I never heard the word loss functions, where it was all about decisions, and I was wondering what you think about that.
Yeah, I mean, that's the same issue. I was really talking much more about inference than decisions, but to me, I mean, when I work on these things, I think the loss functions are in the context of the problem. So I'm not interested really in inferential loss functions like squared error loss. Like I'm not really trying to come up with a point estimate. So if I'm making a decision, then the loss functions would really have to do with what's the cost of making the wrong decision, how much does it cost the company, how many lives are being saved or whatever. And I do think that would need to go in, and that needs to be modeled too. It is a flaw of, if you look at the medical decision-making literature, they tend to just treat all of the losses as known, but in real life, you do often do inferences to estimate those too, and that tends to be ignored. So I agree it's important.
Hello, thank you for the existential angst, but do you have a book or maybe your blog posts, so we can go back to this and with a cool head,
Oh, well, Yu-Ling and I have an article called Holes in Bayesian Statistics, so you can read our article. So that's, and yeah. Thanks for all your questions. Usually people don't ask questions. I appreciate that.
Thanks, Andrew. That was just quite splendid. And, I'm one of those guys who have been reading your book since the first edition. My question is, when I was in my formative years, I had to unlearn a lot of classical statistics that was sort of ingrained into me back in my undergraduate years and masters. And then I started enjoying Bayesian statistics. And so when we approach a problem, there is maybe you would call it I don't know whether you want to call it a bias or something, but how we have been trained or what we have learned that comes into play into our research and how we approach a data analysis problem or an applied problem. From your talk, I want to get your opinion. Do you think the time has come for us to think how we're teaching Bayesian statistics? And that might even include the way BDA 3 has come about. Thank you.
Well, thanks. We're finishing our Bayesian workflow book, so there's some of that. I guess I'll just say at the very practical level that I think experimentation is where it's at. That simulating from the model, simulating from the prior, and making graphs and all that we should be doing that all the time. It should be a lot more routine. So part of teaching that is that not just that you do a demonstration in class, but that the students have homework, and the homework is simulate from this model. It's surprisingly difficult to get things to work out, and so that's my answer.
Hi, Andrew. Thanks a lot for your great talk. I have just a curiosity. You spoke about your, let's say, first meeting in 1991 about the model checking approach. So I was wondering now, what's the feeling now? Prior predictive checks and posterior predictive checks are, let's say, now well accepted by the Bayesian community. What's your feeling in 2024?
Oh, I don't really know what people do. I mean, I think that's, as we get older, we do our own stuff and we become less and less aware of what other people do. But I'm happy to hear that. I mean, I do feel like in some way, just the idea of doing the simulation is so important. It's almost more important that you do some fake data simulation than how you do it. But although I will say, like, back in the day, there were a lot of non-Bayesian papers where people do a simulation study and there'd be a table at the end of the paper with a lot of numbers that were like 0.93, 0.93, 0.96, and like, you know, that's horrible, right? So they weren't really, like, so not every simulation study is good. But yeah, I think simulating and graphing the data is just wonderful, even no matter what people do. I almost like don't care how they do it or even if they're doing it Bayesianly.
You know, that will effectively wrap up the session, a wonderful session, incredible talk, and you know, I think we've heard a compelling case for the importance of data analysis as part of Bayesian statistics from an expert. Please catch him and start the conversations going. Enjoy.
The garden is open for lunch.
Oh, the garden is open for lunch. Oh, wait, but also...
No, that's okay. Just a reminder...
It's working, but everybody's speaking. So
okay. So anyway, there is a session in memory of Ramamurthy right now. Yes.